Good morning. You should see my desktop. Is that what you see? Ooh, seems like only one person's here right now. Do you see the desktop?
Yes, sir.
Okay, thanks. It looks like, let's see, how many people are here right now? It doesn't seem like, oh no, I see. Okay, looks like about half the class is here right now. Okay, well, good morning. What we're going to do is we're going to try to do just like we did in the regular classroom. I'm showing my desktop so that you can see me when I run programs and open text files. And yeah, if I need to draw something, I can draw something, with like a paint program. So we'll just work this way, just like the projector would work. And if while I'm talking, if you have any questions, please just shout out your question. If you type something into the chat, I probably won't see it. It's too confusing to be looking at so many different monitors. So don't type a question into chat. If you have a question, just go ahead and just unmute yourself and just ask the question right away. Okay? So feel free to interrupt me at any time you want. Okay? Um, Anybody have any question right now about what we're going to do today? Any question at all? Okay. There's still actually only about half the class here, so I don't know if people will be coming in as we go along. All right. So, and also this is supposed to be being recorded. If it does get recorded properly, I'll put the recording up on the website, but not right away. That'll probably not till later this afternoon. Because I have a class right after this one, so I probably won't have time to put the video up till later in the day. Okay. So, uh, today wanted to finish two examples from this Java thread zip folder, and then we're going to start talking about the race conditions. Okay, so in this Java threads folder, there's two interesting examples I want to look at. They're at the very end. These two ones that are called experiment, thread 11 experiment and thread 11 experiment 2. They kind of show something that it's a little bit worth being aware of. Okay, remember processes, if you call up task manager, I try to call, let's see, okay, here's my task manager. If you call up Task Manager, you know that processes have a process ID number. So that's this column here. Every process has a process ID number. There also is a thread ID number. Now, Task Viewer does not show you the threads. They'll tell you how many threads, like this process here has 29 threads. This process here has 5 threads, but I can't find out the thread ID numbers of them. Okay, so each one of those 5 threads has a unique thread ID number that identifies that thread to the whole operating system. Every thread has a unique, globally unique thread ID number, just like processes have process ID numbers. Okay, Java has a thread ID number, and it's not the operating system's thread ID number. Yeah, they just refer to it as the thread ID. Let me call up the Java help page on this. So if you go to the oh darn it. Oh, here's the thread class, and there's a method get ID. See? Okay. And there's two versions of it. There's a older version of it and a notice there's this older version of it, and then there's thread ID. That's the newer version. But the newer version is really new, Java 19. So I don't use it because I'm not sure that most people have that recent a copy of Java. They do the exact same thing. If you this description of get ID and this description of thread ID are exactly the same. They return the thread's ID number. See, so long returns a thread ID number, but it's not the operating system's thread ID number. It's not globally unique. Any two Java processes can also have a thread 7. or thread 10. It's a number that Java gives to the threads more or less in what order you create them in. And it's a little weirder than that too. It's not a global thread ID number. It's not the operating system's global number. Okay, let's look at this code here. It's kind of a little bit tricky, but it's going to show you that the thread ID numbers are really kind of weird. I create 3 thread objects. Okay, but the thread objects are a little bit different. Each thread object has a reference to another thread. See, so this thread has a reference to another thread, and this thread has a reference to another thread. And what this thread does is, after its run method is called, it calls the run method in the other thread. So it passes its thread of execution. This thread passes its thread of execution into this thread of thread object. Then this thread object passes its thread of execution into this thread object, and it ends there. So when you call this run method, it will call this run method, and it'll call this run method. Now, is that in 3 threads or not? It's in 3 thread objects, but it would be one particular thread of execution. So what's its ID number? Well, it turns out that it depends on how you ask for the ID number, because the ID number is literally just assigned to this thread object. This thread object has a thread ID number, and this thread object has a thread ID number, and this thread object has a thread ID number. Okay, let me run the program. You'll see the kind of what's weird about the output. Notice it says, I think I'm thread number blah, 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 or maybe I'm thread number blah, blah, blah. And see, it calls the thread ID number 2 different ways. It says, what is the ID of this object? And what is the ID of the current thread? And it does that again here. What is the ID of this thread object? And what is the ID of the current thread? You'd think those would be the same thing. You know, whatever thread is in here, you'd think you'd be getting the ID of the current thread, but that's not what you're, this does not give you the ID of the current thread. This gives you the ID of that thread object. Now, run it. Remember I said that Java threads are confusing. That's why we kind of started with C threads. Java threads do everything in a funny way. Now, so compare that output to the code. So we entered thread 1, and it says, I'm thread 11, or maybe I'm thread 1. I'm thread 12, or maybe I'm thread 1. I'm thread 13, or maybe I'm thread 1. Well, that came from the first time, that's this. This is the main thread, which is thread 1, calling this run method, not as a thread, just calling it. The thread is thread 1, the main thread. When it gets in here and it says, what ID, this is the ID of this object. That object has thread 11. So this thread, well, I should say, this thread object is thread object 11. This thread object is thread object 12. This thread object is thread object 13. The main method is thread object 1. When I call using the main method, this run method, the main thread runs through these 3 objects and reports each object's thread ID number, but it's always the main thread. Then you do the next one. You start T1. So that's starting a thread inside this thread object. That produces I'm thread 11, or maybe I'm thread 11, because this guy starts thread 11. So what happened to threads 9, 10, 11, 12, 13? What happened to threads 2, 3, 4, 5, 6, 7, 8, 9, and 10? Notice it went from thread 1, which is the main thread, to thread 11, which is this first thread we started. I don't know. I don't know where threads 2, 3, 4, 5, 6, 7, 8, 9, and 10 are. Maybe those are the garbage collector threads. I really don't know. It's kind of funny. The main thread is thread 1, okay? And then the very next thread we start is already, oh, sorry, this one. The very next thread we start is already thread 11, okay? Then thread 11 goes into its run method, and that's when it says, I'm thread 11, because that's this is thread object 11. the current thread started in thread object 11, so these are both the same thing. Then he goes down to this thread object. This is thread object 12, but so this get current ID returns 12, but the current thread is still 11 because 11 is threading its way through this code. Then 11 goes down into, see, then 11 goes down into here, and then the current thread object is 13, but it's still thread 11. Okay. Then this guy returns, which means that this thread is done. So that was this thread is done. Now we start a thread in thread 2's object. Now thread 2's object was thread 12 object. So now you get down here. I'm thread 12, or maybe I'm 12. I'm thread 13. So thread 12 starts here. So that second thread we created starts here in thread 12, and he is thread 12, but then thread 12 jumps down into here, which is thread object 13. So then this is thread object 13, but the current thread is thread object 12. Okay, this can get really messy. Probably the simplest answer is don't ever call this, always call this. If you want to know what the current thread is, don't call get ID, which even in the, if you go to the newest version of, don't call thread ID. Okay, you're not supposed to call get ID anymore. You know, as of JDK 19, you're not supposed to call get ID, but that's only if you have JDK 19. Even if you call thread ID, you shouldn't call this dot thread ID. It should be thread dot current thread dot get ID. Current thread is the thread. Current thread says, where did I start? The way to think about current thread is we have 3 thread objects. Each thread object has a thread ID number. Each object has an ID number. If you start a thread in there, then the current thread has that ID number. So wherever it goes, its current thread ID number is where it started. If you start in here, that's thread object 12. The thread that starts in there has its current thread number fixed at 12 from then on. Even if he jumps into here, which is thread object 13, he's still current thread 12, even though he's inside thread object 13. Is this good design? I don't think so, but that's, you know, we write code in the language we're given. So it's very strange. You'd think it was like in C threads, when you ask for the current thread ID, you get the operating system's thread ID. The operating system gives every single thread a unique ID number. In P threads, if you ask for a thread's ID number, you get the operating system's ID number for that thread. Java probably shouldn't have given you the operating system's thread ID number because Java needs to be platform independent of how operating systems do things. So expecting Java to give you the operating system's thread ID number is probably not a good idea. But this system they came up with is just kind of strange. They seem to, why they made a distinction between the ID number of the thread object and the ID number of the current thread is kind of strange. So you have to be very careful. If the bottom line is always ask for a thread. If you need to, and you need thread ID numbers are real useful. It's very useful to know which thread sometimes is doing something. You should always ask for the thread ID number this way. It's a mistake to ask for it this way. Okay. All right. So that's one quirk of threads. The thread ID number is not quite what you think it is. It's the ID number of the object that the thread originated in. That's the best way to think of it. The ID of the object that the current thread originated in. Okay. If you're just in a thread object and you call this, see, this means this object. So you're going to get the ID of this object, not the object you started in. This is the ID of the object you're currently in, not the ID of the object you started in. That's usually not what you want. And maybe in some programs, maybe this distinction is useful. I kind of doubt it, but maybe the people who design Java know something I don't, and maybe they know of examples where distinguishing between where you started and where you are is helpful. But I've never seen any place where it was helpful. But I think this is just a little bit goofy, because that's one thing to look at, right? So now here's another example. This second example is supposed to be an example that helps explain this diagram we looked at yesterday, the thread creation patterns. There's these two thread create. This is the updated picture of the thread creation patterns, and I put a PDF of it in there also. I put it in there as a PDF and as a text document. So uh, this is the current. I updated the picture a little bit to make it a little bit more detailed. Okay, remember there's two ways of creating threads. My task implements runnable, or my thread extends thread. Okay, and this is the better way in the long run. This was designed, I think, to just be a kind of a quick and dirty way to create threads. You don't see it get used much in sophisticated programs, but you see it get used a lot in textbooks for giving examples. So if somebody just wants a quick and dirty example of a thread, they're very likely to do it this way. But if somebody's writing sophisticated thread programs, they're much more likely to do it this way. But a lot of textbooks only do this example because a lot of textbooks just say, "Oh, we're going to give you an introduction to threads," and they do all the examples that they're introductory examples this way, and they don't even get around to this because they think of that as an advanced topic, maybe. Okay, so you have to be familiar with both of these strategies. Okay, now here's a program that's kind of meant to show you how that's working. Okay, what we're going to do is give a thread. Okay, if I go back to this picture, if you do this, in this pattern, there are two run methods. There's this run method down here, and then he overrides the run method from thread, because this is my thread extends thread. So there are two run methods, the run method in this object and the run method that it overrides, which is really there. In the way Java does things, when one method overrides another method, both methods are still there. And in fact, it's not uncommon for the overridden method to make a call to his parent method, because the parent method does some of the work and the overridden one does more work. So both methods coexist. Now, if you go down here, you also have, but here it's more clear, you have two run methods. You have the run method in the thread class, but then the thread class holds a runnable reference to an object holding a second run method. So this has got two run methods, this one here and this one here, one in the thread class, one in the runnable object. And this guy's got two run methods, but the picture doesn't make it so clear. There's this one that overrides the run in thread. Okay. Start starts the run in thread. Well, over here in this picture, start starts the run method in thread. Okay, so start starts this one. It starts a thread of execution in here. But when you're down here, polymorphism kicks in. Starts looking at two thread run methods, the run method in the object with him and the run method that's overridden. By polymorphism, start starts this guy, not the overridden one. Okay. Over here, starts this guy. And as this comment points out, what he does is look for that reference. If the reference is null, he quits. If the reference is non-null, he just transfer control over to here. So his job is to call that one. He doesn't do anything but call that one. Okay. Now, what's interesting is when you're down here, you still, if you combine these two pictures, you can actually give a thread three run methods. So see, this one's null right now. Well, if you make this one non-null, you could have my thread with a non-null reference here pointing to a third run method. I didn't draw a picture of that case because it's, oh no, people probably would think you're nuts to do it, but we're going to do that just to show you can do it. So we can take this picture and combine it with this picture and give this guy a third run method. Okay, and here's what the code looks like. My thread extends thread, but my thread takes a constructor parameter just like thread does, and it just passes it to the super class constructor. What that does is it gives this guy an ability to set that parameter there. I'm giving my thread a try to look at both pictures at the same time. Look at the code and look at the picture at the same time. Okay. So I'm giving my thread this constructor call that lets the superclass constructor initialize this guy to a runnable. Okay, so you give my thread a pointer to a runnable, and my thread will make this point at the runnable. Now then he'll have three run methods. The run method in my thread, which overrides the run method in thread, but then there's also a run method pointed to here, just like there is up here. Okay, then which thread method can you call? Okay, so what we're going to do is we're going to try to call all three of them. Okay, so this is the method that this run method is this one that's overriding the superclass run method. Okay, so it's going to print out its thread ID. Then C, it's going to call the superclass run. Normally, you would never do that because the superclass run only says if this thing's not null, I transfer control to him. And that's what's going to happen here. We're going to essentially, here's the order. This run will be called first. He'll print something. Then he'll call this run second. But that'll transfer control to this third run, and he'll run. So then we'll run all three run methods. But we won't get any output from this one because this is the one that just transfers control over to this one. But we can actually make it so that we can run all three run methods. Okay, and if you compile and run it, you see two of the three run methods. This is run in class myThread, which extends thread. Okay, notice it's the same thread ID. So this is all one thread of execution. So one thread of execution, the thread of execution starts in here. That's the run in class myThread. That'll be the run. No, I'm sorry. It starts here. That's the run in my thread. Then it calls this run. This run detects that this is not null. Now, by polymorphism, this run sees that reference variable. Well, actually, it's the same reference variable. This is just inherited. So he sees that reference variable being not null. So then he calls that run, except that run's really pointed to by it's the same reference variable because it's inherited. So it doesn't matter if you think of it sitting in this picture or if you think of it sitting in this picture. It's the same variable. That is just inherited from up here. So then he will call this one. So we'll go from this run method to this run method to this run method in one program. Okay, that just shows you this picture is real, that this picture really is describing what's there. Again, I keep saying the same thing over and over again. Java threads add a layer of complexity that just maybe doesn't need to be there. P threads are just pure threads. Java threads are threads with a layer of object-oriented programming layered on top of them, which is good. You know, when we talked about passing parameters to threads, the object-oriented nature of Java threads makes it real elegant to pass parameters to thread and get return values from thread. That's where the object-oriented programming part of it really shines. But then they did this. Like the big problem is they didn't need this pattern here. They didn't need two thread creation patterns. They probably should have just ditched this way at the beginning. It just doesn't really serve any purpose, and it adds a layer of complexity for no real good reason. Okay, so so we'll pretty much always use this, but even this one even though right now we're using that one, we can see that even that one still lets us do weird things because because of this subclassing. If they just did this from the beginning, you would never subclass. But since you can subclass, and if you do subclass, you can merge this thing with this thing and get weird things. Yeah. If this if this didn't exist, if this whole notion was not existent, oh, you can actually prevent a class from being subclassed. If you go back to the Java doc, they probably should have done this. When you declare a class, you can declare the class as final. You can say public final class thread. Final means nobody can subclass me. And that might have been a good idea. Yeah, there didn't seem to be any good reason for subclassing thread. Yeah, if they'd have made public final class thread, then you'll see if you look in the Java documentation, you'll see a fair number of classes are final classes where no one's allowed to create a subclass of them. If you try to extend a final class, you'll get a compiler error. Okay, so they could have made thread final and just completely ditch this whole weird my thread extends thread idea and ended up with a simpler design that was less confusing. But this is the way they did it. And I've never seen an explanation. Maybe they have a real good explanation for it, but I've never seen it. And when you read more advanced Java threading books, they tell you use this, don't use this. Yeah, they basically say that explicitly in more advanced books. Just don't use this, always use this. Okay, so kind of weird stuff. Okay, so I labeled these two programs as experiment because they show you weirdnesses of the Java threads. They both represent something that's kind of strange, a little bit weird. So it's more of an experiment. Oh, you would never do what's in these in real coding. You know, you would never pass one thread through a bunch of thread objects and ask for thread IDs. You would never create a thread object with 3 run methods. So I labeled them as experiments because it's just something you would not really ever want to do, but they help explain the nature of what Java threads look like. Okay. Any question about those weird examples? Okay. All right. So let's start talking about race conditions. Okay. Race conditions are hard to define. In fact, I gave you some reading assignments for race conditions. And if you look in all those reading assignments, none of them defined what a race condition is. This one tries to define a race condition, and the definition is wrong. I'll tell you in a minute why it's wrong, but it's not really a correct definition of what a race condition is. And let's see. I have to look in the Wikipedia page. Let's see. I don't think it has a correct. Let's see. Their definition is kind of weird because their definition of actually in this notice that this book they're talking about hardware first. See, in electronics. So race condition, the idea came originally from a digital circuits, and then down here they talk about in software. Yeah, and they don't really give you a proper definition of race condition down here. Yeah. Okay. Like this is a race con this is a ridiculous definition of a race condition. This is closer to the proper definition actually right here. That's as close as they get to giving you the right depth. So leave that highlight. We'll get to it. Yeah, that's closer to what's actually the right definition. Okay, so the best thing to do is just do examples. Okay, um, a race. The what we're going to do is we're going to look at the simplest example of a race condition. It's not going to be what the definition of a race condition is. It's going to be the simplest example you can make of a race condition. And then from this real simple example of a race condition, we can kind of build up on the idea of in general what we mean by race conditions. Race conditions are the single most common problem with multi-threaded code. Multi-threaded code is notorious for having these race conditions, which are in a sense bugs. Not in a sense, they're not it's not clear that a race condition is a bug, but almost always it is. But by even the definition can be kind of ambiguous about this, but for the most part, when people have bugs in their multi-threaded code, more often than not, the bug is a race condition. There is another bug called deadlock, which is also kind of a big problem. Deadlock is the other real big problem that can come with multi-threaded code, race conditions and deadlocks. Okay, so see, I really want to do is draw a picture. I don't know if I can draw a picture on this. Let me think. Well, let's look at the code first. The code, yeah, code takes some looking at. I'm going to have, here's my threads down here. I'm going to always pretty much use the other pattern, a pattern of creating a runnable. I'm not going to create thread. I'm going to, my task is implements runnable. So there's my task implements runnable. There's one of my thread functions. There's my other thread function. Okay. Then I've got these global variables that these thread functions are going to share and manipulate. Okay, so I'm going to create what's called a shared variable. Okay, that's shared by, now, okay, there's three global variables. This variable is going to belong to thread one. This variable is going to belong to thread two. So they're not going to be a problem. This variable is going to be shared by thread one and two. So we call it a shared variable. Shared variables are the source of most race conditions. So I'm going to have two threads that both use this variable. One thread uses this variable exclusively, the other thread exclusively uses this variable, but both threads are going to use this variable, and they're just going to be incrementing. So look down here. The name of this class is race1. So this is how I access the static variable. So that's just accessing the static variable in race1. So the name of the file is class variable. The class is race1. So this variable is race1.count. This is race1.count1. Okay. Then down here, I take race1.count and I increment it. That's the shared variable. And I stick it in a variable, a local variable. So this is a local variable. Okay. So I increment the global variable and put the result. Well, actually, this is a post increment. So really what that means is I grab this variable, stick it in there, then increment it after I've grabbed it. So it's important that I'm using a post increment there. So this line does three things. It reads this variable, writes it to that location, then increments this variable in that order. So in fact, this should be a count. What it does is it reads count, writes old count, inks count. Okay, so three steps, one, two. In fact, what's going to cause the race condition is the fact that there's really these three steps involved here. Read, actually, just read count, write old count, increment count. Three steps. Read this guy, write his value over here, then increment this guy. Okay. Now, that's where the race condition is going to happen. Basically, what the race condition is, there's three steps in here. A thread can stop working at any time. Remember, this is where we go back to what we talked about a lot in the first couple of weeks. Threads are represented by thread control blocks. At any given time, a thread can be taken off the CPU, stuffed into a thread control block, and be put into the ready state and just be blocked and be waiting. And then sometime later, the thread can be pulled out of the thread control block, put on the CPU, and run again. What's going to be weird here is that can happen in between step one and step two. You could read count, then get stopped, because these individual steps are actually individual bytecode operation. This is not what's called an atomic step. This step is done by, essentially, there's going to be a read machine instruction, then a write machine instruction, then an increment machine instruction. So when you look at the compiled code, remember I said, when you do threads, you have to look at computer architecture, assembly language, operating system structure. Threads are hard because you have to think about everything, everything about how computers work. So this single line of code is at least 3 machine instructions: a read instruction, a write instruction, and an inc instruction. What happens if you do the read instruction and the CPU you're taking off the CPU? Okay, so then when you get back on the CPU, you'll start the write instruction. Okay, and then you'll go on to the inc instruction. Or you might increment the read instruction, then the write instruction, then get taken off of the CPU. Okay, okay. Now down here, we have the same thing happening in the other thread. Oops. This line of code is doing the same thing. See, it's using the same variable, okay, and it's reading that variable, writing that variable, and then incrementing that variable. Okay. Now, these are two threads that are simultaneously accessing this one variable. Okay. Now, here's what can happen. This thread reads count and then gets stopped. Okay. Well, actually, let's let him read it and write it. So he reads what's in count and he writes what's in count into old count, and then he gets stopped. So suppose he gets stopped right there. He gets kind of blocked. Okay, so represent that like with a hash mark. Okay, he gets stopped there. So right now he read count and he put it in old count, and then he gets stopped. Meanwhile, oh, and notice this is a loop. Then you go down here and he's looping. Now, what he's doing as he's looping is he reads count, writes count, increments count. Then he loops, reads count, writes count, increment count. So as he's doing this, count is just growing and growing and growing and growing. Okay. Now at some point he gets blocked. It doesn't matter where, just he gets blocked and then he gets back again. When he gets back again, he doesn't realize it, but while he was gone, this variable incremented a whole lot of times by this guy down here. He increments it, and then he writes the new value in new count. And then he's real surprised that new count, no count don't differ by 1. See, if you read this code in isolation, old count is this count incremented by 1. So old count is this thing before you increment it. New count is this number after you increment it. So if you look here, you take this variable, you read it, then you write it into old count, then you increment it, then you take the new value and write it into new count. So in theory, these should only differ by 1. This is just before you incremented it. This is just after you increment it. So they should differ by 1. The race condition is if you get stopped after you read count, if you get stopped anytime after you read count and you get blocked, this guy increments the variable a bunch of, well, actually, no, after you write it. After you've read it and recorded the value in here, you read that variable and record it in there, then you lose the CPU. He increments that counter a bunch of times behind your back. Then you come back, you finish your increment, and then you look at the new value, and you're surprised, how could it not be different by 1? If you looked at this code and asked any programmer, what's the difference between old count and new count, they would tell you it's 1. But if you told them, oh, by the way, this is a multi-threaded program and this is a shared variable, then they hopefully would say, oh, I have no idea what the difference between these two variables are. What's the difference between new count and old count? If you tell a programmer this is a thread, then they would realize that, oh, you could be interrupted anytime in the middle of these steps. So you could have a really old value in old count and a really new value in new count, and they don't have to differ by 1 because your other thread could have been manipulating this count variable behind your back. Okay. Now, this bad situation, no, the bad situation of him not seeing a difference of 1 is unexpected. That's kind of what race conditions are about. A race conditions when he sees something he doesn't expect to see. because of the scheduling, if he sees something that he wasn't expecting, we go back over here, sort of in a sense, he gets an invalid execution. Something invalid is not really the right word, but he gets he gets something he wasn't looking for or doesn't want or doesn't expect. There's really not a real good definition for this. Here they use the word invalid. Well, the execution is perfectly valid. You know, it's the code we wrote, so it's valid. There's no hardware failure. It's just that it wasn't what we want to happen. You know, a programmer who wrote this is really probably expecting that these two variables differ by one. They wouldn't necessarily be expecting that behind their back, this variable changed. Well, this variable changed behind their back in between this line of code and this line of code. Okay. So that's a race condition. You see something you really weren't expecting because of a scheduling. Now, if you never interrupt this, like suppose this guy runs, then this guy runs, then this guy runs, then this guy runs, then you'll never see a race condition. You only see a race condition if this guy should happen to get blocked somewhere after he reads count, or after he writes old count, and before he reads new count. If he's interrupted between this step 2, actually I can make this is step 4 would be read count again. Okay. And then actually a step 5 is write old count or new count. So there's really kind of 5 steps going on. Read this, store it there, increment it, read it again, store it there. 5 steps. If you're interrupted anytime after step 2 and before step 5, then you'll see weird things. If you're interrupted after step 2 but before step 5, you could end up writing into new count a number that's way more than 1 plus old count. Okay. So that's the crux of the matter, is that if you get interrupted in the middle of doing something and you weren't really expecting to be interrupted in the middle of doing something, and then because you got interrupted in the middle of doing something, you get a weird result, that's a race condition. Notice that's a very long-winded thing to say. You get a race condition is when you get interrupted in the middle of doing something, and because of the interruption in the middle of doing something, you get a result you weren't expecting. That's a race condition. Now, if you get interrupted in the middle of doing something, and then he never, like, suppose you get interrupted, but this guy never runs. Maybe there's 2 CPUs. This is running on one CPU. The virus scanner is running on a second CPU. So when he stops running, the virus scanner maybe takes his place. And he's supposed to only have one CPU. He's running, he gets interrupted right there, but then the virus scanner runs. Then you go back to him. Well, he got interrupted, but since he never ran during the interruption, there's no problem, no race condition. The race condition is if he's interrupted and while he's interrupted, he runs, then he will cause a race condition with this one, or vice versa. If he is running and interrupted right there, and then while he's interrupted, he runs, and then you go back to him, he'll see a race condition. So the race conditions only when you interrupt at just the right time and switch between them. Okay. The bottom line is the race conditions don't happen very often. Okay, let me run the program. Now that program ran for, the numbers right now. Okay, the numbers may not mean much to you yet, but let's think about it. The program ran for about 2 seconds. A modern CPU in 2 seconds will do this while loop millions of times, and this while loop millions of times. In fact, you can see down here that this counter here, count 1, is supposed to count how many times thread 1 looped. And this counter is counting how many times thread 2 looped. This counter is the one that they're sharing, but this one just counts how many times it just says, it just says how many times thread 1 loops. And this is how many times thread 2 loops. If you go over here, you see that thread 1 looped 366 million times. And count two looped 345 million times. Okay. Between the two of them, they did over 500 million loops. But the race condition only happened 1, 2, 3, 4, 5, 6, 7 times. Yeah. So in the process of looping hundreds of millions of times, back and forth, back and forth, back and forth here, between here and here and here and here, looping back and forth hundreds of millions of times, the race condition only happened 1, 2, 3, 4, 5, 6, 7 times. So that means the race condition happens once every trillionth of an, out of 300 million executions, we only saw less than 10 race conditions. The race conditions are happening like 1 in every 30 million loops. It's the race condition's really rare. Okay? Now, I can do a little experiment. I can make the race conditions even rarer by making this program run on only one CPU. Like right now, the program's running on multiple CPUs. My computer has this machine has 12 CPU. Well, it has 6 cores and 12 virtual cores. So it really has 6 cores. Remember, we talked about the other day that these cores really come in pairs. They're not really independent of each other. Okay, so I'm running when I run this program, my program can run on any of these cores. But what I can do is I can open a command prompt here. Now go to Task Manager, find that command prompt. He's right there. Tell the operating system that he is only allowed to run on core 6. Okay, so now that CMD is only running on core 6. But that also means the way Windows does it, any process that CMD launches is restricted to core 6. Okay, doesn't matter how many threads it creates. Any process launched now from that CMD, any process launched from this CMD is stuck on core 6. Okay, now I'm going to run that program. And now I'm running that program, even though it's going to have multiple threads, all those threads are going to be running only on one core. Oh, what's that? Oh, I typed out Java C. I meant, I have to run it. So Java race 1. I didn't get a single race condition. See, the race conditions now are so hard to come by because there's only one CPU. So now that CPU would have to interrupt this, out of all this code, it would have to interrupt at just this one place, like, after somehow between steps, it has to be between steps 3 and 4, or between 2 and 5. So right after 2 and between 5, the interruption has to be in that little narrow window. Okay. And the CPU is not likely to get interrupted there when you have one CPU. Let me run it again. See, I didn't get a single race condition. Didn't get a single race condition again. Notice that the looping is happening a lot. 600 million loops on this thread, almost 1 billion loops on the other thread. If I keep doing this, I should get a race condition eventually. Modern CPUs are getting so fast that it's actually getting harder and harder when you run these things on one single CPU, because the CPUs are so fast, they're not likely to interrupt each other. See, I'm not getting any race conditions. Now my program has a race condition, but I'm not seeing them. Okay, now go back to Task Manager, give this guy 2 cores. See, race condition. Now the race condition's in the program all along. The program has a race condition, but when it only runs on one CPU, you rarely see the race condition. Oh, this brings up an interesting story. multiple cores on CPUs started becoming available in about the year 2005. Okay. In the year 2005, when companies started buying CPUs with two, originally, originally you would buy a CPU with 2 cores. Like now, I managed to get myself a CPU with 12 cores. Okay, at one point they only had two cores. And when they first had 2 cores, they really were two independent cores. When they started getting 4 and more cores, then it started becoming ambiguous whether they were 4 independent cores or 2 independent cores with hyperthreading. But when the first two dual core machines came out, they really were 2 cores. Companies all over the place started finding race conditions in their programs because programs that never showed a race condition, all of a sudden they're going, oh, we have bugs in our code that we never knew about. Because you can see here how the program could run happily on 1 core and never demonstrate that it actually has a race condition. As soon as you slap the program on 2 cores, all of a sudden the program's buggy. And there was actually it was kind of there was a transition period for a few years in the early 2000s when companies were going, oh no, we have bugs in our code, we have bugs in our code, and they were discovering race conditions in their multi-threaded programs that they never knew existed because on a single core they were just not that likely, or on a single core the race condition would show up once a year and they just go, huh, okay, it crashed, so what? They'd have no idea what caused the crash. Because the race condition might show up just once in a blue moon, and they had no way to know what might even cause the crash. But then once they started running on 2 cores and programs started crashing left and right, they would realize they have a race condition. So you can see it's interesting to see that the race condition depends a lot on how you run the program. If you run the program on multiple cores, oh, if I run the program on 3 cores, it will not increase the number of race conditions. Like if I go back over here and go to Task Manager, if I give this guy 3 cores, that's not going to increase the number of race conditions. Okay. Because it really just means it's only the fact that you can switch between. I have 2 threads. So 2 threads, all I need is 2 cores to get race conditions. If I was having 3 threads, then a third core might introduce more possibility of race conditions because there'd be more freedom to do more scheduling. But right now, since I only have 2 threads, if I give it 3 cores, it's never going to run on 3 cores simultaneously. It's only ever going to run on 2 of those cores. So I'm not going to see more race conditions. Well, I did, but that may have just been a coincidence. See, that was just a weird quirk. See, just that one time I happened to get a lot of race conditions. I got for some bizarre reason, I got a huge number of race conditions a lot. That one run produced a huge number of race conditions. Not clear. It's not clear why that might be. Okay, then here's another one. See, back to just a few race conditions. A fair number of race conditions. Medium number of race conditions. Medium number. So you notice that the number of race, see, now, there was a small number of race conditions. And then if I go back to one single core, if I go back to one single core, doesn't matter which core it is. If I go back to one single core, I may see a race condition. Boy, on this CPU, I don't need, yeah, a few years ago, when I had slower computers, I'd see like 2 or 3 race conditions. When I ran it on one core, I would usually get at least 2 or 3 race conditions. Here, I'm not getting any. Yeah. So when I run this particular code on this CPU as fast as it is, it just it just never manages to do an interruption with the perfect timing of interrupt this guy right after here, interrupt him right between here and here, and then run this guy while this guy's interrupted right at that one point. You'd have to interrupt him out of all the byte codes that make up this code. You'd have to interrupt him right between these 2 byte codes that do the write and, well, that do the ink and the read. So you actually only have 2 byte codes where you could do the interruption when you have only one CPU here. Okay. All right. So what's a definition of race condition? Roughly, it's when different schedulings cause a problem. If now If I actually don't care about this, then it's not a problem. Okay, if I don't mind this output, then I don't have a race condition. Yeah, I would say this is a race condition only if I thought this was a problem. Yeah, so what is a race condition kind of really depends on whether you think the uh let's go here. Let's go to this. A race condition occurs if the effect of multiple threads on shared data depends on the order in which the threads are scheduled. Okay, so the results we got over here depended on the order of the scheduling, but it's only a race condition if we don't like the result we got. If we don't care about the different effects, it's not a race condition. In fact, this is a very bad definition because by this definition, almost all programs have race conditions. Almost all multi-threaded programs will have different results when you run them different times. They almost always have. This is the definition of what's really called non-determinacy. This is the definition of the fact that if you run the program, you might get different results. But non-determinacy is almost by definition what we mean by multi-threaded. It's only a race condition if you don't like the result you saw. If the the effect you see If the effect you see is something you're not happy with, then it's a race condition. If the effect you see doesn't matter to you, then it's not a race condition. Okay. Well, as we go along, we'll see some examples of what I mean by that. A race condition is pretty much this definition, but with a little added clause. A race condition occurs if an unwanted effect, yeah, I mean, you might put it, if a race condition occurs if an unwanted effect of multiple threads on shared data depends on the order in which the threads are scheduled. It's only if the effect you see due to the scheduling is unwanted that you would call it a race condition, a bug. If you don't mind the difference, then it's okay. Here's a famous example of a race condition that's not a problem. Okay. Suppose two people submit a job to the printer at the same time. Okay. What could happen? In the old days, you could actually have one page from one person's output, then one page from the other person's output, then one page from the other person's output, then one page from the other person's output, because the two things were trying to print in the printer at the same time. That would be an unwanted race condition. Now, suppose person A's paper came out, 10 pages, then person B's 10 pages came out, versus person B's 10 pages came out first, then person A's 10 pages came out first. Is that a race condition? Well, the effect of the multiple threads that do the printing, well, the shared data could be they're printing the same document. They could be printing the same document. It could be a shared data. So two people are printing the same document at the same time. Depends on the order in which the threads are scheduled. Well, it's not a race condition if person A's document comes out, then person B's document comes out, or the other way around. That's not a race condition because there's nothing wrong. You expect one document to come out, then the other document come out, but you don't know which one's going to come out first. You don't know which one's going to get scheduled on the printer first. If two people print documents at the same time, one of them gets printed first, then the other one. If the printer really did print a few pages of one document, then a few pages of another document, then a few pages of another document, that would be an unwanted effect of the scheduling. That would be a true race condition. And there was a time when printers were really bad like that. Like on a DOS machine, if you printed two documents back in the old days, if you tried to print two documents at once, they could just get garbled up. Okay. And we will see that later on in the output on the console window. If two threads print to the console window simultaneously, their output will get garbled up. So if two threads print to the console window, if we don't do something to help, the output of the threads will get, well, we saw it already. We did see that when we were doing earlier. We would see garbled output. We were getting race conditions. The shared data was the console window in that case. When two threads shared a console window, the console window is essentially the shared data, and they printed to the shared data, we would get weird outputs that in a sense could be called race conditions because if you really wanted one person's output to be separate from the other output, then having them jumbled up isn't good. But this definition would call a printer a race condition because a printer is just going to schedule one paper to be printed, then another paper to be printed. You have no control over which one gets printed first. You don't know if three people print at the exact same time the same document, you don't know which one's gonna whose paper is gonna come out first. That's not a race condition because it's what's expected, not something unexpected. So if you add one word to this, a race condition occurs if an unexpected output of multiple threads, well, if the unexpected effect of multiple threads on shared data depends on the order in which the threads are, yeah, something like that. Essentially, the race condition has to be something you didn't want because you will get effects that depend on the scheduling. Effects that depend on the scheduling are ubiquitous. You actually can't, you don't even try to avoid them. Nobody is going to try to write a printer that somehow guarantees, what order the papers come out of the printer in. It wouldn't be worth the effort and it would be pointless. If three people send a paper to the printer at the same time, they just come out in some order. Nobody really cares what order they come out in, as long as they don't get jumbled up, as long as you don't get pages from one paper mixed up with pages of the other paper. Okay, so same here. Let's see, same here. He uses the word invalid execution. Well, that's what I would say. What he really means to say is you get unwanted effects. You know, they're not invalid's a bad word. I mean, what do you mean by invalid? When we run these programs, the computer is doing exactly what we tell it to do. There's nothing invalid about what's happening. The computer is behaving exactly the way we programmed it to. We programmed it with a race condition. It's not invalid. It's just not what we wanted. So this is kind of, it gets at the kind of hints at the idea. I would change invalid to unwanted. You know, Critical race can cause unwanted execution, or unexpected execution. Invalids may just not, but that's the closest. That's pretty close to the right idea. The execution you get is somehow not what you want. Okay. It depends on the scheduling, the output, like he says here, the scheduling, the output depends on the scheduling, which is okay, but you want it to be a race conditions when that output is not what you want. It depends on the scheduling, but it's what you don't want as opposed to just, oh, it's okay. Okay. Now let's keep looking at some other examples. Close that. So that's race conditions are caused not always, but mostly by shared variables. There's no race condition on this guy because only thread one ever touches that guy. There's no race condition on this guy because only thread two ever touches that guy. There's a race condition on this guy because thread one and thread two both share him, and they could, they could be in the middle of doing something with the shared variable, like here. They could be in the middle of doing something with the shared variable, get interrupted, and then they weren't really expecting that. So then when the other person accesses the shared variable, then you come back to here, they see the shared variable is essentially weird from their point of view. The shared variable magically changed values in the middle of doing this line of code. In our case, in the middle of this line of code, that variable changed values magically. Okay, it was actually changed by this guy, but to this code, that would be a race condition. Okay, the shared variable causes the race condition. Okay? Let's look at another example of a race condition. Try and remember what's different in this one. If you want to know what's different in two programs, you can, I don't even remember now if you can compare them, diff them. Oh, uh, now I remember. The difference in how the threads are stopped. The one we just did, I stopped the threads by using another global variable. See this run flag, which is a Boolean? Down here, he looped while the run flag was true. And he looped while the run flag was true. So when the run flag, so what the main thread did was the main thread went to sleep. Well, the main thread, the run flag starts out true. The main thread launches the two child threads. The main thread sleeps for 2 seconds. Then the main thread sets the run flag to false. Then he waits for them to notice that the run flag is false, so he ends this loop. He notices the run flag is false, and he ends this loop. Okay, this is kind of a quick and dirty way to stop threads. You give the threads a flag that they can watch. Now, there's a kind of funny thing in here. See that word volatile? Remove the word volatile, run this program. Guess what? This program's in an infinite loop right now. We'll talk about this later. We have to learn what this word volatile means. What happened? Now my program's I need to kill this program. It's in an infinite loop. Right now, we have 3 threads. The main thread, this thread, and this thread. There's actually 3 run flags, but you don't realize that until you start studying threads better. There's 3 run flags because each thread has its own cache. And what happens is when the main thread sets the run flag to false, he's setting his copy of it to false, and no one's informing these other 2 threads that their copies should be updated to false, and you get a weird situation. This has got to do with effects of threads on caches. So Java provides a word called volatile. When you provide the word volatile in there, what happens is Java now knows that that flag needs to be updated in all the threads simultaneously. So when this thread sets run flag to false, the Java virtual machine makes sure that this guy gets the default value and this guy gets the false value. If it's really weird, like there's a volatile keyword in C++, and it doesn't mean the same thing. This is one of the crazy things about this stuff. Is C++ has a volatile keyword. It does not mean the same thing as Java's volatile keyword. If you forget that volatile keyword, you would never guess that this program never sees the run flag change. And it's only because of the way the modern CPUs use their cache. Okay, so this is actually considered, this is an old-fashioned way of stopping threads. And it's kind of not a good way, because if you don't remember this volatile keyword, you have a real big problem. So here's another way to stop threads. So this other program kind of uses a more modern way to stop the threads. It launches the 2 threads. It launches the threads, then it sleeps, then it interrupts the threads. Okay, we send an interrupt signal to each thread. So we say thread 1, interrupt them. Thread 2, interrupt them. Then we wait for them to notice that they've been interrupted. And then here, instead of saying while, see over here, it was while run flag is true. Now it changes to while I'm not interrupted. Okay, and the interruption is taken care of by the Java virtual machine. It doesn't need that volatile keyword. It's much safer. The interruption is fairly safe. These runtime flags are not really, you'll see them a lot in textbooks. This idea of using a run flag to tell threads when to stop, using a flag to tell threads when to stop. You kind of see that in a lot of textbooks. It worked on older CPUs, but modern CPUs, with their heavy use of cache, it doesn't work anymore. Well, it works if you remember to put volatile in there. But if you forget the volatile, then it won't work. This is the more modern way to stop threads. You interrupt the thread, and then the thread can check if he's been interrupted. And if he's been interrupted, he can just stop running. Okay, so that's the only difference here, is that this uses a kind of bad old-fashioned way to stop the threads. This uses a more modern way to stop the threads. Okay, and otherwise this one runs the same. It still has the race condition. That time I got a fair number of race conditions. That time I got very few race conditions. I'll almost all, yeah. You'll always get race conditions. See, oh, no, actually, I wonder if you could actually get this thing to run with no race. That time was only one, two, three, four, five, six, seven, eight, nine race conditions. Yeah, out of, oh, look at this guy incremented almost 1 billion times. They incremented, modern CPUs are unbelievably fast. So these loops happened nearly 1 billion times. We're talking large numbers here. This thing looped nearly 1 billion times, and this one looped itself 1 billion times, and we only got 7 race conditions in that billions of loops. Okay, so but I'll bet I always going to get a race condition. I'd really be really, really, really surprised if those threads manage to run without any single race condition. Okay, great. Let's see. Now let's look at it. I'm trying to remember what's different about this. Okay, let me go back and do a comparison. Huh. Oh, I'm drawing a blank. I can't. I offhand. I don't even remember what's different here. See, the main method is the same. See, look at. Is there a difference in the thread functions? The only difference is this line of code here. Oh, this gives you a little pulse to the program. Yeah, see, pulse. Yeah, I created a this just lets you know when as the program's running, it kind of gives you a timer. So it prints out these ampersands to give you a feel for where the race conditions are happening. So it kind of gives the program a pulse, so to speak, that every 10 million iterations, it prints out an ampersand, whereas this guy prints out a period. So the pulse of this thread is an ampersand, and the pulse of this thread is a period. And see how that pulse happens? See all those um, all those race conditions happened between a pulse. See, these race conditions happened between two pulses. So one thread had died, gave its last pulse, and then the other thread kind of kicked in and started, you know, incrementing things. And then at the end, there's a lot of pulses. I'm not sure why there's all these. See, notice that there's a lot of pulses without any race condition between them. Okay, so it just gives you this is meant to be kind of, you can't really watch threads. So the idea is to try to give you something that you can get a sense of what's going on. Notice that how there's at the end, there's no more race condition. Notice how the race conditions tend to occur early, and then at some point they stop. So you get lots of pulses at the end where there's no race condition. So we'll pick up there at the timer. Let me turn it off. Okay, so we'll stop there and we'll keep playing around. We're eventually what we're going to do is we're going to create a few more examples of race conditions, more sophisticated race conditions. Then we want to figure out how to get rid of them. When you have a race condition, what you need to do is find a way to get rid of the race conditions. That's the synchronization. So right now, these guys are unsynchronized. Uh, we're going to see that what we need to do is basically say, when this guy's in the middle of this, nobody should interrupt him. Or when this guy's in the middle of this, nobody should interrupt him. So we need to synchronize them instead and make this not interruptible and make this not interruptible. Okay. So any questions? Any last minute questions? Okay. So we're done. Have a nice weekend, and I'm going to end the meeting now. And like I say, if this thing recorded properly, like I hope it did, I'll try to put the recording up on the course website, but it won't be up there till later in the day. But that depends a lot on whether the recording actually managed to get recorded properly. Okay. All right. Thank you. And see you on Monday, I hope. Bye bye. Oh, now I forgot how to turn off the. Oh,